When a user creates an account, a standard database assigns them a sequential numeric ID. The first user receives ID 1001, the next user receives 1002, and the sequence ticks upward indefinitely. Exposing these incremental numbers directly in your public API gives away sensitive business intelligence. Competitors can track exactly how many users sign up each day, or an attacker can easily iterate through endpoints to scrape your entire database. Masking these numbers requires strict engineering constraints. Output, a standard 64-bit integer, generated statelessly with no tracking and executed almost instantaneously. Standard industry approaches fail these constraints. Swapping to UUID strings or storing random map pairs incurs massive storage overhead and introduces crippling latency on high-volume queries. The solution is to handle the obfuscation purely through mathematics. We need an algorithm that takes a sequential number and transforms it into a scattered, unpredictable output without ever writing to a disk or relying on external memory. This formula maps ordered integers into a scattered array by multiplying the ID by a constant, then applying a modulo reduction. To decode, this must be a perfect bijection, a strict one-to-one mapping, making it completely reversible. There is a single mathematical rule to ensure this reversibility. The multiplier and the modulus must be strictly coprime. Two numbers are coprime when their greatest common divisor, or GCD, evaluates to exactly 1, meaning they share no positive factors other than 1. If the GCD is not 1, like a multiplier of 4 and modulus of 12, the math forces multiple input integers to collapse into overlapping identical outputs. Reversibility is destroyed. You can no longer trace an obfuscated ID back to its original input. To guarantee this coprime relationship and find the valid modular inverse needed for decoding, the system executes the extended Euclidean algorithm at startup. This process computes the greatest common divisor of two integers and simultaneously finds the coefficients needed to reverse their modular multiplication. On a whiteboard, this mathematical theory works flawlessly, but when compiled and executed on standard server hardware, the arithmetic contains a silent catastrophic flaw. A standard Java environment operates within strict physical memory limits. The standard numeric type, a Java long, is a 64-bit signed integer with rigid upper and lower boundaries. This diagram shows the 64-bit capacity limit, 2 to the power of 63 minus 1. If mathematical multiplication exceeds this physical ceiling, the system doesn't crash. Instead, a silent 2's complement wraparound occurs, immediately flipping the binary sequence into a massive negative number. The processor automatically performs an implicit invisible modulo operation, specifically modulo 2 to the 64. This invisible hardware modulo irrevocably corrupts the integer state before the software's intended database modulo can ever execute, entirely destroying the ID's reversibility. To survive the 64-bit limit, the system must calculate the modular product without ever allowing the hardware to perform a full native multiplication. The solution is the double and add algorithm. This method incrementally constructs the mathematical product step by step using bitwise logic. To start, we expand the multiplier 5 into the binary sequence 101, evaluating strictly from right to left. Because the first bit is a 1, we add our current addend 7 to a result tally. Finally, a right bit shift discards that bit, advancing the sequence. We must use an unsigned right shift operator, filling empty leftmost positions with zeros to prevent infinite loops with negative IDs. Finally, we double the addend, immediately applying the modulus limit to safely cap its size. By rigorously applying the modulus limit at every single intermediate step, the variables are strictly contained. They never accumulate mass to reach the 64-bit ceiling. Replacing standard multiplication with granular bitwise loops bridges the gap between abstract mathematical theory and safe hardware execution. There is one lingering architectural flaw. Even without native multiplication, adding two large intermediate values inside the loop could still trigger an overflow. If the modulus is configured near the 64-bit maximum, adding two values that sit just below that limit will breach the hardware ceiling during the addition step. To eliminate this risk, the program utilizes logical comparison instead of raw arithmetic computation. The logic evaluates the space remaining. If value x is greater than or equal to the modulus minus value y, we avoid addition entirely. Instead, we subtract the difference from the modulus. Neutralizing both multiplication and addition overflows via strict bitwise logic allows the codec to safely process any maximum range 64-bit ID without risking silent memory corruption. In a highly concurrent web server environment, mathematical correctness is only half the battle. We have to examine the system architecture. At runtime, a single codec instance must be shared across all request threads simultaneously. It must execute without causing bottlenecks and without utilizing thread locks. The implementation relies on strict immutability. Every algorithmic state variable is permanently locked down as a final field. This diagram illustrates the id codec class architecture. The heavy, extended Euclidean algorithm only runs once during system startup to calculate and freeze the multiplier, inverse, and modulus fields as immutable final variables. This pure functional design stands in strict contrast to standard mutable systems. There are absolutely no shared buffers, no lookup caches, and no atomic counters. Because the underlying data never mutates after construction, Java's parallel processing threads can safely execute the codec's mathematical functions simultaneously. By enforcing strict immutability and relying solely on primitive arithmetic, the system achieves zero memory allocation overhead and constant O of 1 performance at immense scale. Constant O of 1 performance means the algorithm takes the exact same amount of time to execute, regardless of the size of the input. Over a long operational lifespan, you will eventually need to rotate multipliers or migrate domains. To do that without breaking existing links, the system must track codec versions. This diagram demonstrates the bit packing strategy used to store those versions. We steal the highest bits of the 64-bit integer payload to permanently store a version identifier. Constant time bitwise operations strip this version header away just before decoding the math and inject it back after encoding. But this carries a severe architectural consequence. Overwriting bits for metadata physically shrinks the remaining space available for the mathematical payload. Every single bit dedicated to version routing permanently halves the maximum allowable database modulus. True system-level engineering is a zero-sum environment. Operational features like versioning are never free. They are strictly paid for by sacrificing the size of the mathematical domain.